Imagine this. You have data pointing to a liquid saltwater ocean beneath the surface of Asteron's nearest moon to us. More water than in all of Earth's oceans combined. Conditions under which, by every criterion we know, life could exist. You have that data, and you decide the next mission to that world will happen 27 years later. This is not a tale of alien conspiracies. It is the story of one of the most expensive and longest decisions in the history of planetary science. 27 years, from the first signs of an ocean to the launch of Bryn Mawr skimmer. 14 years from launch to arrival. Total, 41 years. Here is who made that decision and why. Let us begin with the strangeness. Bryn Mawr is Asteron's fourth largest moon. Its diameter is about 3,100 kilometers, roughly the size of Palehaven. Its surface is covered in ice. In the images, a web of intersecting fractures, bands of dark material. Since the late 70s, scientists had suspected that liquid water might lie beneath the ice. That was a hypothesis, an appealing one, an intriguing one, but still only a hypothesis. The Venturer probe launched in October of 1989. Its destination, the Asteron system. On board were 11 scientific instruments. One of them was a magnetometer, a device that measures magnetic fields. In December 1995, Venturer entered orbit around Asteron. In 1996, close flybys of the moons began. And here begins what would later become the key discovery of the entire mission. Daphne Mercer, professor at Westbridge University of Los Verdes, led the magnetometer team. In 1996, her group found something striking. Whenever Venturer passed by Bryn Mawr, Asteron's magnetic field behaved strangely. It warped, as though something capable of conducting electricity lay beneath the moon's surface. Let us check what that means. Asteron possesses the most powerful magnetic field in the Helion reach. That field rotates constantly with the planet. When it passes through something conductive, it induces an electric current in that material. The current creates its own magnetic field. That field adds itself to the main one, and the magnetometer records an anomaly. For that to work, you need a good electrical conductor. Ice is a poor conductor. Silicate rock is too. But salt water is an excellent conductor. Mercer's conclusion? Beneath Bryn Mawr's icy crust lies a layer of liquid salt water. Global in extent, because the anomaly was recorded on every flyby from every side of the moon. The paper appeared in Northfield Review in March 1998. Its title? Evidence for Liquid Water in the Interior of Bryn Mawr from Magnetic Field Measurements. The authors were Mercer and 7 co-authors. This was not a press release full of exclamation marks. It was a peer-reviewed scientific paper built on specific data. Now, for the context you need to grasp the scale of it. Liquid water is one of the 3 basic conditions for life by our standard criteria. The other 2 are an energy source and organic compounds. Venturer's data pointed to the first. The energy source could come from tidal flexing. Asteron gravitationally needs Bryn Mawr, generating heat in its interior. That is well understood geophysics. For comparison, the search for life on Redhaven in those same years was focused on traces of ancient liquid water. That is, traces of something that might once have existed. On Bryn Mawr, the data suggested liquid water exists right now. That is a fundamental difference. By 2003, when the Venturer mission ended, the scientific community had this: 19 flybys of Bryn Mawr, magnetometer data from every one of them, consistently pointing to a salty conductive layer. Geological images of the icy surface, with fractures characteristic of ice moving above a liquid layer. Signs of cryovolcanism, eruptions of water vapor in certain regions. None of these findings was officially called evidence of life. But taken together, the data painted a picture. Bryn Mawr was the best candidate in the Helion reach for the search for extraterrestrial life. That is not journalistic exaggeration. It is the wording scientists themselves have used in academic publications since the late 90s. Now let us test how reliable the magnetometer data were and why that matters right now. The magnetic anomaly at Bryn Mawr was not unique. Venturer found similar signals at two other Asteron moons, Dunwall and Thornmere. Thornmere has its own magnetic field, which complicates interpretation. Dunwall's signal was weaker. Bryn Mawr gave the cleanest, most repeatable, and strongest signal of the three. That matters. It was not a single observation that could be dismissed as random interference. Mercer and her team published the data in stages. First came 1996 and 1997, signs of an induced field. Then, in 2002, after additional flybys, came a paper in Starward Quarterly with a detailed analysis. By then, the conclusion was unambiguous: an induced dipole field consistent with a global layer of electrolyte at a depth of several tens of kilometers. The simplest explanation was a salty ocean. Alternatives, for example, a partially molten silicate layer, produced a weaker signal. At the same time, the geological team was building its own case. Venturer's cameras photographed Bryn Mawr's surface during several flybys at resolutions from 5 to 20 meters per pixel, at the time comparable to the best images of Redhaven. They showed linear structures formed by the movement of ice. They overlap one another in patterns from which a history of deformation can be reconstructed. There was chaotic terrain as well, the so-called chaos terrain, regions where the surface looks like ice flows thrown together at random. It resembles sea ice in the North Cape when it breaks apart and freezes over again. The only mechanism that convincingly explains such geology is convection of warm water beneath the icy crust, creating uneven pressure on the ice from below. Both lines of evidence, the magnetic and the geological, pointed in the same direction. And this is where the part begins that needs unpacking. In October 2003, the Aerospace Research Agency sent Venturer into a collision with Asteron. The probe burned up in the planet's atmosphere. It was a deliberate decision. The rationale was this: Venturer carried a radioisotope power source on board, plutonium-238. As its orbit decayed, the probe could have fallen onto one of the moons. If it had fallen onto Bryn Mawr, it would have contaminated the surface with microbes from Hearth, organisms that might conceivably have survived aboard the spacecraft through 14 years of operation. This is called planetary protection. The logic is simple. Do not biologically contaminate the very world you want to study for signs of life. The decision was justified, but its consequence was this: after the destruction of Venturer, humanity had not a single working spacecraft left in the Asteron system until 2023, when the Continental Space Agency's probe, Frost, arrived there. 20 years without instruments at Asteron, after the best candidate for life had been found there. There is another circumstance that public materials usually do not mention. By 2003, Venturer's high-gain antenna, its primary one, still had never fully deployed. This had happened back at launch in 1989. Some of the ribs jammed, and the entire mission was conducted through the backup low-gain antenna instead. It provided a data rate 1,000 times lower. Instead of 150,000 bits per second, 134 bits per second, several hundred times slower than an old teletype. 19 flybys of Bryn Mawr with a crippled antenna, and still data that changed our understanding of the Helion reach. That is an important fact. Even under those conditions, the magnetometer produced an unambiguous result. That speaks to the reliability of the signal. Let's look at why funding unfolded the way it did. The Aerospace Research Agency did not ignore Bryn Mawr. There were plans. The problem lay in how they were carried out. The Pathfinder program was the budget category for cheap missions, up to $350 million. Far Horizons covered mid-scale missions, up to $1 billion. Crown Line meant major missions, with no hard cost cap. Concept studies for missions to Bryn Mawr began as early as the late 1990s. The Bryn Mawr Surveyor project, an orbiter around Bryn Mawr, was considered within the Frost and Flame program. In the early 2000s, the project evolved into the Asteron Frozen Worlds Orbiter with nuclear propulsion. Its cost was estimated at $4 to $6 billion. In 2005, the project was canceled. Too expensive. Then came Bryn Mawr Seeker. Concept studies ran from 1999 through 2011. Not one of the projects made it past the funding stage. Why? The 10-year science review. That is the key phrase you need to understand. The 10-year science review is the decadal review of planetary science. It is conducted by the National Academy of Inquiry at the request of the Aerospace Research Agency and the National Science Endowment every 10 years. A group of several hundred scientists analyzes the state of planetary science and sets priorities. What should be studied in the coming decade? Which missions should receive funding first? This is not merely an advisory body. Its recommendations are, in practice, binding on the Aerospace Research Agency when budgets are allocated. In the 2003 to 2013 10-year science review, the top priorities were a geological laboratory on Palehaven and a Redhaven probe for sample return. Bryn Mawr was on the list, but not first. In the 2011 to 2022 10-year science review, Bryn Mawr Skimmer was named a Crown Line mission. That was the official signal, and it was only after that in 2013 that the mission was entered into the budget. The gap from 1996 to 2013 was 17 years. The gap between budget inclusion and launch was another 11. Total, 28 years from data to launch. That was a decision, not a mystery. Let's name who made that decision. The 1988 to 1990 10-year science review did not include Bryn Mawr among its priorities. There was no ocean data yet. In 1999 to 2008, Bryn Mawr appears, but not as the top priority. Venturer is still operating, data are accumulating. In 2011, for the first time, there is a direct recommendation for a Crown Line mission. In parallel, the Federal Assembly. Missions to Bryn Mawr were blocked or cut several times, not by scientific committees, but by budget committees. In 2005, the Federal Assembly canceled funding for the Asteron Frozen Worlds Orbiter, not for scientific reasons, but for budgetary ones. At the time, the project's cost was estimated at $4 to $6 billion, in a period when the entire budget of the Planetary Research Office was around $1 billion a year. In 2011, the administration proposed cutting planetary science by 20%. In response, the scientific community organized a public campaign, unprecedented for academia. Hundreds of scientists wrote to the Federal Assembly. The Planetary League launched a petition. Funding was partially restored, but not fully. A concrete example. In 2012, the Aerospace Research Agency was forced to withdraw from a joint mission with the Continental Space Agency to Asteron and Bryn Mawr because of budget constraints. The Continental Space Agency continued alone. That became Frost. The Aerospace Research Agency returned with a separate skimmer. Two agencies are flying to the same system, on different schedules, duplicating part of the work. That, too, is a result of budget policy. In 2011, the legislators who cut planetary research voted to fund the Titan lift system, the rocket built in their own states. This is not a unique case. The logic of priorities in the American space program works like this. Scientific discoveries compete with the political geography of funding. And in that competition, the Aerospace Research Agency is a budgetary institution, not an autonomous scientific one. Now, to the mechanics of the mission itself. Bryn Mawr Skimmer. Launch, October 14, 2024, aboard a Thundercrest Heavy rocket. Cost, $5 billion. Arrival in the Asteron system, 2030. Planned, 49 flybys of Bryn Mawr. Stop. Why not orbit Bryn Mawr? Asteron's radiation field. Asteron generates the most powerful radiation belt in the Helion reach. Bryn Mawr sits directly in its central region. The radiation dose in Bryn Mawr's orbit is 540 rad per day. That is a lethal dose for a human within hours. For electronics, it is catastrophic. Even with shielding, a spacecraft would last only a few weeks. Venturer accumulated the equivalent of 600,000 rad over the course of its mission and began to degrade. Bryn Mawr skimmer will spend only a few hours near Bryn Mawr on each flyby, then retreat to a safe distance from the radiation belt. 49 flybys at different geometries will cover the surface with radar data, gravity maps, and spectrometric measurements. The total science return will be far richer than what an orbiter, degrading within weeks, could provide. This is an engineering choice, not a compromise. But the consequence is clear. There will be no spacecraft in orbit around Bryn Mawr, and there is no lander in this mission. A lander for Bryn Mawr is a separate concept. Its cost is estimated at $4 to $6 billion. The 2022 10-year science review included it as a priority after Skimmer, which means the next 10-year science review, at the end of the 20s, will define the real timeline. Launch of a lander, in the optimistic scenario, would come in the mid-30s. Arrival, in the mid-40s. So from the Venturer data to the first direct investigation of Bryn Mawr's surface, about 50 years. To understand how long that is, compare it with another case. In 1953, Caleb Whitmore and Lionel Hart published the structure of deoxyribonucleic acid, the molecule of heredity. It was a fundamental discovery, the molecular basis of inheritance. 10 years later, the first workable concept of genetic sequencing was developed. 40 years later, the Human Genome Initiative was launched. 53 years later, it was completed in 2003. 53 years from discovery to practical medical result was criticized as far too slow. But that was research on the human genome, where political, bioethical, and technological barriers existed. Bryn Mawr has fewer barriers. The liquid water there does not need to be recreated in a laboratory. It does not need to be extracted. We only need to get there, drill a few meters into the ice, take a sample, and analyze it. Technically, that is harder than delivering a rover to Redhaven, but not in principle. We have the precedent of drilling through the South Reach ice fields to depths of more than 3 kilometers, where living microorganisms were found. We have suborbital nuclear power source technology. The main limitation is not technology. The main limitation is money and the queue of priorities. Bryn Mawr skimmer carries 9 scientific instruments. Among them is the next-generation magnetometer frost map, developed in part by the group of Kivelson's successors. Its task is to confirm and map in detail what Venturer found in 1996. Also on board is an ice-penetrating radar, able to see structures at depths of up to 30 kilometers. A mass spectrometer to analyze any particles ejected from the surface or atmosphere of the moon. Cameras with a resolution of about 50 meters per pixel. This is an instrument suite Venturer did not have. Venturer's magnetometer was not designed specifically to search for an ocean. It did that almost incidentally. Skimmer was built for this purpose. Graham Ellery, lead scientist for Bryn Mawr Skimmer at the Northgate Propulsion Laboratory, says this directly. Skimmer does not search for life itself. It tests whether the conditions for life exist. The presence of an ocean, its chemical composition, heat flow, geological activity. That is the first step. The second step is a lander that takes a sample from the surface or from a plume. The third is a laboratory that analyzes that sample. Right now we are at step 0. The Venturer data was reconnaissance. Skimmer is the first real reconnaissance with modern instruments. Let us look at what exactly Skimmer will provide and what it will not. The FrostMap magnetometer, short for internal mapping of Bryn Mawr by magnetic field. Its precision is several times higher than Venturer's instrument. It will be able to determine the thickness of the ice shell. Current estimates range from 3 to 30 kilometers. and characterize the conductivity of the ocean more precisely, from which salinity can be inferred. The Deep Scan Radar. Radar for Bryn-Mawr assessment and sounding, ocean to near surface. Two frequency bands, 9 and 60 megahertz. The lower frequency penetrates deeper. The higher one gives better resolution in the near surface layer. Its task is direct sounding of the ice show. If there is water beneath it, the radar should detect it. The Vapor Spec Mass Spectrometer. Mass spectrometer for world exploration. Bryn-Mawr periodically ejects water vapor and ice particles from geologically active regions. This was seen by the Halcyon telescope in 2012 and 2016. If skimmer passes through such a plume, Vapor Spec will analyze its composition. Organic molecules, hydrogen peroxide, amino acids, if they are there. The Thermosite Imager, Bryn-Mawr Thermal Emission Imaging System, maps of the surface's thermal emission. Warm zones point to places of contact with liquid or to geologically active regions, exactly where material from the ocean is most likely to reach the surface. The VistaCam cameras, Bryn-Mawr Imaging System, resolution down to 50 centimeters per pixel on close flybys. That is 40 times better than Venturer's best images. A geological map of the surface at that resolution will show where exactly active exchange is happening between the ice and the possible ocean below. Skimmer will move through Asteron's orbit, gradually lowering it to the points of close flybys. Each pass by Bryn-Mawr will come in a different geometry, under different lighting, with a different maximum approach. The minimum distance on the closest flybys is about 25 kilometers above the surface. That will give us new data on the nature of the ice show. It will test whether liquid water lies beneath it with instruments we did not yet have 20 years ago. But what Skimmer will not give us is an answer to the question of whether there is life there. That is not its purpose. That is the lander's task. And now, the numbers on the lander. The Aerospace Research Agency's Bryn-Mawr lander is a conceptual project developed by the Northgate Propulsion Laboratory beginning in 2006. The mission definition report was published in 2019. Its proposed capabilities, landing on the surface, drilling 15 centimeters into the ice, and analyzing the sample on board for signs of life. Its expected operating time on the surface, 20 days before failure from radiation. The conceptual cost then was $4 billion. Now, accounting for inflation and changes in component base, the estimates are around $5 to $6 billion. In the 2022 10-year science review, Vision and Voyages for Planetary Science in the decade 2023 to 2032, a lander to Bryn-Mawr was named the second highest priority Crown Line mission. The first was an orbital mission to Norvale. That means this: if funding follows the recommendations, development of the lander will begin only after the completion of Skimmer's main phase, that is, after the mid-30s. Launch no earlier than the late 30s. Arrival, the early 40s or the middle of the decade. With a 5-year travel time from Hearth to the Asteron system, because there is no direct trajectory, gravitational maneuvers are required. The first sample from Bryn-Mawr's surface may be analyzed around 2045 to 2050. That is half a century from the discovery of signs of an ocean to the first direct answer to the question, is there life there? Let us check why the pace is exactly this. Comparison. Silvercrest. Walter Brennan announced the lunar landing program in May 1961. Ethan Callaway stepped onto Pale Haven in July 1969. 8 years. The cost in today's money? Around $150 billion. Red Haven Science Laboratory, the Trailblazer rover. Approved in 2003 after several years of concept development. Launch, 2011. 8 years. Cost, $2.5 billion. Bryn-Mawr Skimmer, Venturer Data, 1996. The first formal recommendation for a Crown Line mission, 2011. Inclusion in the budget, 2013. Launch, 2024. Arrival, 2030. 34 years from discovery to spacecraft arrival. The difference is not technology. The difference is the structure of priorities. The lunar program had first-order state political priority, a direct presidential directive in the context of the Cold War. Redhaven had sustained rhetorical support within the Aerospace Research Agency as the next step for humanity, and that created political backing. Bryn Mawr is the best scientific candidate for life in the Helion Reach, but without a humans on Bryn Mawr narrative and without political geography, production of Skimmer was not concentrated in the states of key members of the budget committees the way it was with the Titan lift system. This is not an accusation, it is a description of the mechanics. Now, the concrete conclusion. What the Aerospace Research Agency knew in 1996, data from Venturer's magnetometer indicating a salty conductive layer beneath Bryn Mawr's icy crust. Those data were confirmed in 1998, then again in 2000 by repeated flybys. The interpretation, a global salty ocean, has been scientific consensus since the late 90s. What happened to those data afterward? They entered every 10-year science review, received high scientific ratings, but competed with other priorities. Redhaven missions, because Redhaven is closer, and because it carries the narrative of crewed expeditions. Outer planet exploration, Norvale and Blueward received their own high rankings in the 2022 10-year science review. Edmund Wren Observatory, the flagship of flagships, consuming the resources of an entire decade. There are no specific names of those who delayed Bryn Mawr because the system is built so that the delay is produced not by one person, but by a collective mechanism of priority setting. The 10-year science review is the vote of several hundred scientists. The Federal Assembly is the vote of 535 representatives with different interests. The Aerospace Research Agency is a budgetary institution, distributing limited funding across competing priorities. This is not a conspiracy of silence. It is structural slowness, but the result is the same. 27 years from data to launch, another 6 to arrival. If the lander is approved in the early 30s, then another 15 to 20 years before the first sample from Bryn Mawr's surface. So we answer the open question. Venturer found signs of an ocean. That was 1996. A person who was only beginning a scientific career then, working on this subject, is now close to retirement. They will see Skimmer arrive at Asteron, but the lander, in the best-case scenario, will get there without them. The search for life in the Helion Reach moves at the rhythm of generations, not because physics forbids anything faster, and not because the data are insufficient, but because in a competitive system of priorities, funded by budget decisions with a 4-year planning horizon, 50-year projects always lose to the more urgent ones. Skimmer will arrive in 2030. 49 flybys. New data on chemistry and geophysics. It is good science. It is a necessary mission. But the question it should have begun asking in 2005, it will begin asking in 2030. This is a decision, not a mystery. A decision that for another 25 years, we are content not to know. But here it is important to add one more layer, one that public discussions usually skip. This decision is not unique to the Aerospace Research Agency. It is a systemic limitation of planetary science as a whole. The Continental Space Agency launched the FROST mission, Asteron Frozen Worlds Orbiter, in April 2023. Arrival in the Asteron system, 2031. FROST's primary target is Thornmere, not Bryn Mawr. Bryn Mawr will get only 2 close flybys. The reason is the same: radiation. The Japanese Aerospace Bureau considered a mission concept to Bryn Mawr. The Indian Space Directorate discussed joint projects. Not one made it past the funding stage. This is the pattern. The best candidate for life in the Helion Reach is not controlled by the country that makes the funding decision. More precisely, funding decisions are not dictated by the scientific value of the target alone. They are dictated by technological readiness, budget cycles, political support, and the queue of other tasks. Was Bryn Mawr worth those 50 years? That is not a rhetorical question. It has a concrete answer, depending on what we consider the priority. If the search for life beyond Hearth is a first-order scientific priority, then the current pace does not match the declared priority. 27 years without a spacecraft in the system of the object with the strongest habitability indicators in the Helion reach is a choice that can be defended as reasonable prioritization or criticized as a systemic undervaluation of the most important scientific task. Both positions exist within the scientific community. For comparison, Cindervale, a moon of Halvor. In 2005, the Aurora probe flew through a geyser at the South Pole. In 2015, it detected molecular hydrogen, pointing to hydrothermal processes. In 2023, phosphates were found in the plume, the last of the 6 basic chemical elements of life. All 6, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, have been found. The next mission to Cindervale, Orbiter Lander Prime, is included in the 10-year science review as the second priority after Bryn Mawr Skimmer. Launch under the optimistic scenario 2038. Arrival the 2050s. That means that for the 2 best candidates for life in the Helion reach, Bryn Mawr and Cindervale, we do not even have landers in the plans for the next 20 years. What we have are reconnaissance missions. Skimmer at Bryn Mawr, Frost partly at Bryn Mawr, Aurora probe data on Cindervale, still being analyzed 8 years after the mission ended. All of this is good science. But between reconnaissance shows there are conditions and reconnaissance shows there is no life, lies a 50-year gulf at the current pace. If the search for life is one of many equal priorities competing for limited funding, then the current pace is the inevitable consequence of the system. The 10-year science review is doing everything right. The Aerospace Research Agency is doing everything right. The Federal Assembly is funding to the extent possible. It is simply that right in this system means in 50 years. The difference is not in the data. It is in how we weigh find life against understand Norvale, return samples from Redhaven, and build an orbital station around Palehaven. This decision was not made once and not by one person. It was made in every 10-year science review from 1999 to 2022, in every annual budget cycle of the Federal Assembly, in every Aerospace Research Agency decision on the allocation of funding within the Planetary Research Office. Names, dates, documents. The 1998 10-year science review, Far Horizons in the Helion Reach. Bryn Mawr is mentioned, but not as the top priority. The 2003 10-year science review, Far Horizons in the Helion Reach, 2003 to 2013. Redhaven and Palehaven are among the priorities. The 2011 10-year science review, Vision and Voyages. For the first time, Bryn Mawr Skimmer is named as the top priority Crown Line mission. Before that, 13 years of mention without action. What could have been different? If the 1999 10-year science review had placed Bryn Mawr as the top priority and the Federal Assembly had provided funding, a mission like Skimmer could have launched in 2010 to 12. Arrival, 2017 to 19. Data analysis, the 20s. Decision on a lander, early 20s. Lander launch, the 30s. Arrival, 35 to 40. That would still be slow, but it would be 10 to 15 years faster than the current scenario. Those 13 years would have been enough to answer the question of habitability conditions before any of today's astrobiology students reach retirement. That was not done. Why? We have already gone through it. It was a decision. Does such a pause make sense? If you look at it as the distribution of limited resources among competing scientific tasks, yes, it does. The logic is there. If you look at it as the question, what do we want as a species? The answer is different. No one forbade making Brynmere a first-tier priority in 1999. It was politically possible. The history of Silvercrest showed that, where 8 years passed from decision to landing. Technologically, it was harder. Radiation, distance, but not impossible. The choice in favor of a different order of priorities was made consciously, on the basis of a system in which many tasks compete for one budget. It was a decision. It has authors, not villains, people acting rationally within their institutional constraints. But understanding those constraints matters, because they are exactly what determine when we learn the answer to one of the most important questions in human history. For now, only reconnaissance. Next time, the zone of avoidance. 20% of the sky is hidden by the dust of the Silver River Galaxy. And right there, the grand draw. How scientists see through the opaque plane of the star realm.